Chen from Academy of Mathematics and System Science, Chinese Academy of Sciences. He will speak on Jordan property of automorphism groups of surfaces of positive characteristics. Okay, let's welcome him.
Thank you very much for the introduction, and also thank you very much for invitation. Okay. All right. So this talk is over an algebraically closed field of any characteristic. So we are interested in automorphism groups and birational automorphism groups. So here is a simple example for these Riemann surfaces or smooth projective smooth projective curves. So if genus is 0, that's P1, and if genus 1, that's elliptic curve, or genus greater or equal to 2, that's general type curves. So Kodaira dimension is negative infinity, 0 or 1. And automorphism group here is clear and equals to the birational automorphism group, which is PGL2. So here I stated over C, or any field PGL2 over K. And here is an elliptic curve, a semi-product, some finite group. Here depends on the field. And yeah, in general type curves, that's a finite group, this automorphism. This is a well-known fact. So also, people also interested in some open varieties. For example, affine spaces. If we consider automorphism of AN, so for algebra, it's just a K automorphism of this polynomial ring of n variables. So if n equals 1, this is clear. The automorphism just linear. It's ax plus b. A is non-zero and b is any element in this field K. If n is 2, this is also clear. So there's an algebraic proof. The generators are linear. Linear means belongs to GL2 K, composed with this so-called upper triangular automorphisms. That's x maps to x plus fy. Fy is a polynomial of y, and y maps to itself. So for n greater or equal to 3, the generators is not clear so far. So if the elements is a composition of this linear or upper triangular, is called 10, but also conjecture to exist some wild automorphisms. So here I want to say there is also algebraic geometry proof for this automorphism of A2 by minimal model program. For example, I remember that's Takahashi, probably master thesis, a student of Professor Kawamata. He gave a proof for this automorphism of A2 by using toric geometry. And it can be found in this Matsuki's book, Introduction to Mori Program. And also, I think Lamy and other dynamic algebraic geometers, they also try to prove this for general, more general open surfaces. So for projective space, let's recall. So the automorphism of Pn is just in Hartshorne's book, that's PGL n plus 1. We denote the birational automorphism group of projective space by Riemann group of rank n, CRn. So if CR1 just automorphism of A1, that's PGL2, that's the automorphism of P1. So another standard fact of this generators for Riemann group of rank 2 is PGL3, that's automorphism of P2, linear part, and this quadratic transform. Okay. So in this talk, we interested in special property of this automorphism group or birational automorphism group called Jordan property. So let me introduce this property. So Popov gave this name. A group, this is abstract group. A group gamma is called Jordan if there exists a constant J, which depends only on this gamma, such that any finite subgroup of gamma contains a normal abelian subgroup of index at most J. So this definition is if you the first time see, you will feel very strange. So there exists some constant J only depends on gamma, and for any finite subgroup contains a normal abelian. Normal can be removed, just contains some abelian of index at most J. So in 1878, Jordan showed that general linear group GLN has this Jordan property. So when he studied a differential equation called Fudge's differential equation. And in 2009, Sal studied this problem, and oversee, he can prove by the algebraic geometry of surfaces, he can prove the Kreimana group of rank 2 also has this Jordan property. And he proposed in this paper is any Kreimana group of rank n Jordan? This is a question. Let me introduce some known results we have so far over the field of complex numbers. So first, Chen and Deqi Zhang, they proved over the field of complex numbers, automorphism of a smooth projective variety has this Jordan property. And Zahin showed, he actually constructed if X is an abelian variety times P1, and this abelian variety is dimension greater than 0, then the birational automorphism group of X is not Jordan. Popov actually classified surfaces over C whose birational automorphism group has Jordan property. Actually, except this one, except Zahin's example, the other cases of surfaces or the birational automorphism all has Jordan property. And Prokhorov and Shramov and Jinsong Xu, they proved if X is a threefold over the field of complex numbers, then birational automorphism group is not Jordan if and only if X is birational to P1 times E. E here is an elliptic curve cross F and over G. That's E cross F quotient G, Gx faithfully on this product. Or this is P1 times of abelian surface. They actually classified for these for threefold, which the birational automorphism is not Jordan. And Jinsong Xu also conjectured if X is an abelian variety over an algebraically closed field of any characteristic, the birational automorphism group is not Jordan if and only if X is birational to some variety having a faithful action of a non-trivial semi-abelian variety. So semi-abelian means a torus times abelian variety. So he conjectured this one, and only up to dimension 3 over C it is known. So another property we can use birational group or automorphism group, the property to study the geometry of this variety. For example, Jin Song Xu proved there exists a constant Rn such that for any n-dimensional rationally connected variety, X over C, if birational of X contains a subgroup G isomorphic to Z quotient P, quotient PZ to n's for some pi P greater than Rn, then X is rational. So roughly means if this birational automorphism group contains a very large order finite group, cyclic finite group, then X is rational. Okay, so let's recall the proof of this. So the cells problem now is a theorem. Cells, he asked, is Kreimana group of rank n over C is Jordan. He proposed this and proved n equals 2. Pronkroff and Shremov proved this for n equals 3, and assuming BAB conjecture, and this proof, this is Jordan for any n. But after Bika showed this BAB conjecture, and then this problem knows. So Kreimana group is Jordan. But we know Kreimana group is a very large group, much larger than automorphism. So outline of proof, and we will use this idea later to prove the impositive characteristic for n equals 2. So let me sketch the proof. So suppose we take a finite subgroup G of Kreimana group of rank n. There exists the G equivariant blowing up. So we can assume there exists a smooth projective rationally connected variety W, such that G is a subgroup of this automorphism of W. So which means, so first we consider from Pn to Pn is a birational group, birational automorphism. We try to resolve its indeterminacy and get a automorphism from W to W. So here we need to do some blow-ups. So we can only get W is rationally connected. Then we can run a GMMP on this W. So since W is rationally connected, so this GMMP over C always terminates. And then we will get a Fano variety or a Fano Mori-Fano fibration. So in this case, this Fano variety may not be smooth anymore. This W is smooth, but this X is not smooth. But the singularity is not too bad because we are running from smooth. We will get terminal Fano or a G Mori fiber space Y to Z, such that G is a subgroup of automorphism X or G is a subgroup of automorphism Y by the results of BCHM. Then we know that by BAB, now we know that by BAB, this terminal Fano variety form a bounded family. So there exists some M and capital N and the degree D, such that this negative MK embeds all Fano varieties into a big projective space P to N, and with bounded degree. The degree of X is less or equal to D. So in this case, actually, we know that this is a canonical embedding or anti-canonical embedding. Then this automorphism of this X actually is a restriction of automorphism of Pn to its image. So in this case, since we know this GLN is Jordan by Jordan original results, and it's not difficult to prove the automorphism of Pn also has Jordan property. You can either use this adjoint representation, embed this PGLN to some very large GL, like n squared, some large general linear group. You can show that also has Jordan property. So in this case, we can show this automorphism, this G already has this Jordan property. But the other thing, I think the condition before, in the definition of this Jordan property, he actually need to find some invariant points under this group action. So how can he find? So first, since this GLN plus 1, we just canonically view this G in best to GLN plus 1. So since this is Jordan, as Jordan's results, then there exists a constant L such that there exists a normal abelian group G1 with index at most L. Then we can take K invariant, G1 invariant hypersurfaces or hyperplanes, actually hyperplanes, H1 to HK, such that X intersect H1 to HK has only finitely many points, P1 to PR. Since we assume the degree of X is less or equal to D, then this R, the number of points, is less or equal to D. Then we can let G0 to be stabilizer of 1 point P1. So it's easy to see the index G1 over G0 is less or equal to R, and by assumption, less or equal to D. Okay. Then we can somehow run induction of dimensions for Mori fiber spaces, for G Mori Fano fibrations. And over C is easy to see Z is also rationally connected, but with dimension less than dimension Y. So by induction, there exists this is a concept similar to the definition of Jordan property. You can see that you can find a subgroup. You can find a subgroup of this G, which has a bounded index and abelian. It has a fixed point Q on this C. And then we can consider the fiber over this Q. And then we need to, the fiber over this Q is a Fano variety. Then we need to show on this fiber, there exists a fixed point over Y. So in the end, the Jordan property guarantees there exists and the boundedness of these Fanos guarantees there exists some fixed point by this group or by this subgroup with bounded index. Then for this fixed point, we can embed this G0 to this tangent space of this point, the TPY, the tangent space. So since the tangent space of that's a vector space of dimension n, so G0 is actually embedded into GLN. So here is a typo. So X faithfully on this tangent space, but then G0 will embed it to this GLN, not equal. This is a typo. And then we apply the Jordan property of GLN, then we can get G0 also has this Jordan property. So this is rough idea. So here we see how to use it. I think this is just a generalization of Cell's original proof for Cremana group of rank 2 plus boundedness results of epsilon LC Fano varieties. Okay, now we are interested in if
question.
Yes.
So what's the upper bound for this index J? So in this case, Cremana N.
Cremana N. This is
by
inductive.
definition,
yeah.
By definition, there is some index, some constant, constant J. So what's this number? Is there any conjecture on this?
I don't know if there is an effective bound for this because this argument runs induction. But for lower case, I think rank 1 or 2, there are. For example, let me see. we can find some constant, yeah, some constant for rank, lower rank, and n equals 1 or 2.
Okay.
Yeah. But not
okay.
very...
So for shared proof, it doesn't work for quantitative P, or?
In sales proof, no. I think sales proof in characteristic P. So first, the Jordan Jordan property is not hold anymore.
Oh, okay.
Yeah, so
okay.
So the other thing
okay.
is boundedness. So here you need to use some argument like G equivalent resolution. I'm not sure if it is it holds for any dimensional positive characteristic field. The other thing is boundedness for Fano varieties. I don't know if it holds for dimension 3 in positive characteristic. Yeah.
Okay. Thank you.
Okay. All right. So then we try the purpose of this project just try to study similarly for positive characteristic. Is there this Jordan property also holds, or is there, if it does not hold, can we find a similar property for this Jordan? So first, let's see a simple example. If P, let's assume the characteristic is positive, is some prime P. So actually this from the classification of finite subgroup of automorphism of P1, we will introduce later. So this example shows automorphism of P1 is not Jordan already. So say let K be the algebraic closure of Fp. Fp is a finite field of P elements. Then we know Fpn is just a finite field of Pn elements. So there is a fact, actually this is a simple PSL2 Fpn are simple, or for almost all n greater than 0. I think maybe for n greater or equal to 3. This is called simple group of Lie type something, or one of these. So so for almost all n, these are simple. So you can see that this PSL2 apparently are finite subgroup of this PSL2 Fp bar, but these are simple. So in the definition of this Jordan property, the normal subgroup either trivial or itself, but itself is not abelian, so a trivial group. But you can choose very large n, such that index also goes to infinity. So this example shows the automorphism of P1 is not Jordan for this K is algebraic closure of Fp. So then we need some new definitions. We need some new definitions for this Jordan. I think this definition first I saw from Hu Fei's results paper. I don't know if it was introduced before or so. A group. So first, a generalization is like this. Since there are some problem because of this characteristic P. So first thing is we don't consider this P subgroup. So which is called generalized P Jordan. If there exists a constant depending only on this gamma, such that every finite subgroup G of gamma, whose order is not divisible by P, contains a normal abelian group of index at most J. So in this definition, we actually exclude P groups. We don't consider these P groups. We can similarly define, this is called generalized P Jordan. The other thing is we consider this P Jordan, P groups, but we take another constant called E, and the P0 subgroup. So this definition seems also natural. So if there exists some constant J of gamma and E of gamma, depending both only on gamma, such that every finite subgroup G of gamma contains a normal abelian group of order coprime to P, but index at most J times this is the order of P0 group, the power to E gamma. So this is another definition for P Jordan. So P Jordan, we need two constant, one bound this index, the other bound the order of these P groups and power. So apparently from this definition, a Jordan group implies it is P Jordan, and P Jordan group implies it is generalized P Jordan. So okay, then we can introduce some facts over the characteristic P. So from the original proof of Cell, actually his proof already showed Cremana group of rank 2 is generalized P Jordan. And from these people, and also Brown, Fate, Larson, Pink, or Hu Fei, over the positive characteristic field, this generalized general linear group GLN is P Jordan. So every linear algebraic group, which is a subgroup of this, also is P Jordan. And in a work of Hu Fei, 2018, he actually showed for any projective variety over a field of positive characteristic, algebraically closed field of positive characteristic, automorphism group is P Jordan. That's his, I think that's the main theorem of that paper. Okay. So in this talk, X is a projective variety over field K. So here we use this to denote automorphism group scheme. So which is a functor, odd X, a functor induced by X. This points just for any S denotes to odd of X over S, X times S over S. This automorphism. This functor is representable by some group scheme called odd X, and we use odd X. This just introduce the. We just interesting is abstract group. So we take all k points of this odd X. And in the end, we need some Kodaira dimension. So Kodaira dimension argument. So for safety, we need to assume the projective variety over K is smooth. Then we can use this. We can define Kodaira dimension. So the starting case, the baby example, just the curves in positive characteristic. So smooth projective curve, if C is P1, then we can show this is P Jordan. Actually, we will show later. Then this is P Jordan by the classification of finite subgroups of this automorphism of P1. If C is an elliptic curve, then this one is Jordan. So either you can show it. Automorphism of C is just the K points of C. This is translation, semi-product group automorphism, which is a finite group. Then you can use this exact sequence to show this. But actually, we will show later general results for any abelian variety. The automorphism of this abelian variety is Jordan. So this one would be clear. If C is a general type curve, then we know this is a finite group. And then it's apparently Jordan. So because it's already a finite group. So, okay, so in this case, automorphism of P1, there is a classification, and first we saw it on a paper of Dolgachov and some other. Which is similar to that of over the field of complex number. So let's C be a finite subgroup of PGL2, and GP denote the P0 subgroup. Then G is one of the following. So first is this dihedral group D2N, and this is A4 and S4 or A5. And these are PSL2, just as we mentioned before, this PSL2 FPN and PGL2 FPN. And a group of the form GP, this is a semi-product, this Z quotient MZ. M is a positive integer, which is coprime to P. So from this classification, actually, we can verify one by one this automorphism of P1 is P Jordan. Actually, we can also find the precise upper bound for this index and the index J or E from this classification. Because it's some computation I will not show here, just idea. And for general type varieties, we know there is a classical results by Matsumura. He showed general type variety, this automorphism is finite. And we can just quote his proof similarly. So if in positive characteristic, so Kx is big, then this would induce a birational map. The image, the closure of image will be denoted by Z. So since this is induced by Kx canonical bundle, so this automorphism will contain in this automorphism of Pn. And another thing is the Kodaira dimension greater or equal to 0, and we also need this later. This automorphism does not contain non-trivial connected linear algebraic group. So this is a fact, actually can prove not difficult. So otherwise, if this automorphism contained some non-trivial connected linear algebraic group, it must have some dimension, positive dimension. So we know that for linear algebraic group, dimension 1 is either Gm or Ga. So if it contains this Gm or Ga, you can use some geometric quotient method, which is proved by Popov. Then this X is birational to some Y possibly singular, X birationally to Y times P1. So in this case, even X is singular, then you can use some elementary argument to prove if X is birational to Y times P1, X is smooth, then Kodaira dimension of X has to be negative infinity. Then this would contradict to the assumption X is of general type. Then we know the auto 0 just trivial, so which means auto is a finite group. So this is a rough idea, and this idea we will see later. Kodaira, that's a Kodaira dimension argument. Okay, so for abelian varieties, we can show if X is abelian variety, then the automorphism of X is Jordan. The proof is as follows. So first, classical results of abelian variety automorphism, just translation and semi-product gamma. Like what is gamma? Gamma is actually the invertible elements of home or endomorphism of X to X. So from this Mumford's book, the endomorphism of X to X is just it's just a subgroup of this home, a Tate module of L, ZL to ZL. Then you take invertible elements, so you can show gamma is actually isomorphic to a subgroup of GL2N, ZL. L is a prime number, which is not divisible by characteristic of K. So first we know this is this structure, automorphism is like this. The other thing is for the we need to know the finite subgroup here has an upper bound. This is ideal goes to Minkowski or Searle. The finite subgroup here, you can do a natural map. Just take GLNZL to GLNZ quotient LZ, this map. So you will show this finite group which restrict on this finite group which has trivial kernel. So, but then the upper bound for the finite group here goes to upper bound of this finite subgroup. But this one is a GLN over some finite field, so this would be easy to compute the upper bound. Then you just need to avoid some characteristic. You assume L is 3 if P is not 3. If P is 3, just let L is 5. So you take any finite subgroup of this automorphism, of this automorphism X. First, you intersect with X to K, which is K points of X. But this one is abelian. This is an abelian group. So GX is an abelian group. And G quotient GX is a subgroup of this gamma. It's a finite subgroup of this gamma. But we already know by the previous argument, there exists an upper bound for this finite subgroup, which means the index of this GX has some upper bound. So this is the proof. Now we will introduce our main results. So here we just main results actually contains two parts. One is this and some birational automorphism group of surfaces. The other just to try to find the best possible bound for this index or for this E. Let's involve some computation, and so I will not introduce that part. So I will introduce this part, the Jordan property. The first results is similar to these Hu-Fei's results. So let's recall Hu-Fei showed if X is a projective variety, then this automorphism is P Jordan. So here, if we assume X is a smooth projective variety of Kodaira dimension greater than 0, then this automorphism is Jordan. So we can just drop the P. But if this Kodaira dimension is less than 0, we already know like automorphism of P1 is P Jordan, but not Jordan. Okay. So first, there is a property, or we can say a lemma, which frequently used in the proof of this Jordan property. Suppose we have a left exact sequence, 1 to gamma prime to gamma double prime. So we actually want to prove gamma has some property like Jordan, P Jordan, or generalized P Jordan. So if we know gamma prime has this property, and gamma double prime has the property of bounded finite subgroups. Bounded finite subgroups means there is an upper bound such that any finite subgroup of gamma double prime is the order is bounded by this upper bound. So this is bounded finite subgroups. So okay, so we put, so let's see this last line, the last exact sequence. We put automorphism here. We know there's a standard 1 to odd 0. To odd 0, just recall the odd of this functor, odd x, is a group scheme. You take the identity component, and in positive characteristic, it may not be reduced. So you also need to take its reduced part. Then you take k points. So you got this one. So you have a natural exact sequence. We try to show this one has Jordan property, and this one is we will see later. This is already abelian. So, and this one has bounded finite finite subgroups. Okay, so there is a classical result says odd quotient odd 0 has bounded finite subgroups. It is proved in and Deqi Zhang's paper, put in some remark, or Hu Fei also quote this result. The other thing is Brian showed if gamma is a connected algebraic group, and suppose gamma does not contain non-trivial connected linear algebraic subgroups, then gamma is a group of points of some abelian varieties. So from this fact, gamma does not contain some non-trivial, then this is linear. So this argument is similar to before. If it contains some non-trivial connected linear algebraic group, then Kodaira dimension would be negative infinity. So it shows this is a group of points of some abelian variety. In particular, it is abelian itself. So this is already an abelian group. You take any group here, you just intersect with it. And the quotient actually lies in here. But this one already has bounded finite subgroup property. So the index is bounded. So first we need to prove, we need to use this argument to prove the automorphism is actually Jordan. The other things I will say later. So first we will consider birational automorphism group of surfaces. So over algebraically closed field, we first consider smooth projective surfaces. So we know in positive characteristic for surfaces, a lot of things is good, like resolution works, and also minimal model program works, similar to over a field of complex numbers. Sorry. Okay, so we can prove similarly to Popov's result. If S is birational to a product of an elliptic curve times P1, then this birational automorphism group is not generalized P Jordan. That's the not so good case. In other cases, so if the Kodaira dimension of X is negative, but X is not birational to this product, elliptic curve times P1, then the group of birational of S is P Jordan. So if Kodaira dimension is greater than 0, actually by the previous result, in this case, the birational automorphism group of S is Jordan because we can reduce to minimum model and then we can show. So this is similar similar result as Popov. So
Christian, so for the previous result, so you do not need to assume S is small.
In previous this one?
Yeah, in this one. No. In second. Yeah, in this one, because all the statements are birational.
Oh yes, you are right. You are right. We don't need the.
But then you need to use some. You need to use the main result one or in the proof.
Proof. Proof. I will introduce later. You mean which one?
This one. Yeah. For this result, you use the main result, the first result.
Yes. For this one.
Yeah. But
birational as actually you can take a minimal model. That's birational of minimal surface. But for minimal surface, birational is just automorphism.
Okay. Okay. Thank you.
So I actually will prove in the end, but I first skip. Okay, so yeah, the classification just similar to this, but if Kodaira dimension non-negative, the minimal surface exists. So here we need similar argument. This is you can, if you are interested, you can find this in, for example, standard textbook of positive characteristic surface like Bodasco. You can find all the proofs. And if collider dimension is negative, then S is either rational or birational to C times P1. C is a smooth projective curve, could be P1 or any genus. If collider dimension is 0, then S is either a K3 surface, Enric, abelian surface, hyperelliptic elliptic curve times other and take a quotient, or quasi-hyperelliptic. Quasi-hyperelliptic, then this fibration, if you consider the Arbanese map, the general fiber in this case is singular. It can only happen in characteristic 2 or 3. Okay, so here we actually quote some result, but we didn't go further. We did not, in this paper, we only interested in Jordan property, but actually a lot of mathematicians already studied a lot for automorphism of surfaces in positive characteristic. They studied very explicitly and even give some classification or some tables. For example, if collider dimension 2, that's nothing to say, just in this case, birational equals birational as minimum is automorphism. So general type surface is just finite. If collider dimension greater or equal to 0, as far as I know, for example, for automorphism of K3 surfaces over a field of positive characteristic, Professor Dogachev and Chen, I think they have several papers to study this subject and give some sort of classification. And Martin recently, last year, he gave some classification of these quasi-hyperelliptic surfaces. And Gu Yi, I think he also introduced his result in this East Asia algebraic geometry seminar for his classification of these elliptic surfaces of collider dimension 1. So he told me he's also working on this quasi-elliptic fibration of collider dimension 1. He's also working on that. It's an ongoing project. So these statements are very explicit. So we here we can use, if we are only interested in Jordan property, we just use the previous results. And I want to mention there exists a lot of work in this subject already. Okay, so the last thing, let's go to the proof of this birational automorphism group of surfaces. So first, Zahin's construction for birational of this group, automorphism group, is not generalized Jordan, can be actually moved to almost identical to in positive characteristic. You just be careful, you choose some L, which is not divisible by P. So in his proof, he actually first choose an abelian variety, A, because this is construction for any abelian variety times P1, A, and he choose some special ample line bundle, L, and in a prime number L, little l, I just choose another. So line bundle L and another, say A, okay. So he considered the translation, pull back this L is also equivalent to L. Maybe I will write down it's better. So, but okay. I will introduce the rough idea. Just choose a abelian variety A, and he constructed a special line bundle L. So actually, this L over A is a A1 bundle. So you can actually, from the birational automorphism group sense, you can consider the total space of this L to the total space of this L, the automorphism. You can consider this one. So then he constructed for any L not divisible by this P, this there exists some finite subgroup, the index is L. So this would contradict to the Jordan property. And for this Cremana group of rank 2, this is P Jordan because this is contains automorphism of P2, contains automorphism of P1, so cannot be Jordan. So this proof essentially due to cell and also the previous argument by this run this minimal model program. Either you get the piezo surface or a P1 bundle. So in both cases, you can find some bound. In this case, the bound can be, if you choose carefully, you can find a effective bound, but may not be sharp. The last case, we know that in this case, with the last case, if S is birational to C cross P1, C is a general type curve, then we have a natural exact sequence. This is birational of S, and this one is a birational automorphism group of fiber P1. So which means you fix the base because here you have a projection C cross P1 or S to C. So this fiber-wise, the birational automorphism is naturally a subgroup of this. And gamma is just a subgroup of this automorphism of C, of this curve C. But we know that this C is a general type curve, so this is a finite group. So by the lemma before, we already proved this one is P Jordan, and this one is finite. So in particular, bounded has bounded finite subgroup property. So we get this one is P Jordan. Okay. I think that's all. Thank you very much. I will stop here.
Okay. Is there any question?
Hello.
Yes.
Hello, Ife. So I think you consider the mainly focus on the birational automorphism group of the surfaces, right? Of surfaces. So as you have mentioned in the previous slides, so the only negative case is when S is birational to elliptic curve and the product with P1. So if you consider about the automorphism group of not necessarily projective surface, so if S here is not projective and you consider the automorphism group, so can you get some result like auto S has to be P Jordan or generalized P Jordan?
I think here we cannot get a better result than Hu Fei's. So Hu Fei showed for only.
But he showed the S is projective, right? But
you are saying
S is not projective. Yeah, here my S is not projective, but you consider automorphism of S, not birational automorphism.
I see. I didn't consider this open surface problem. But you are saying if S is like some affine or not net or quasi-projective surfaces, right? You consider automorphism group of S. What kind of property you can get? Is it your question?
Okay.
No, I haven't considered this problem.
Okay. Thank you.
So other questions or comments?
Maybe I have one question. So do you have other question, other examples of coordinate dimension negative, such as automorphic group is still Jordan? Yeah, you have many counter examples. Yeah. You can produce many counter examples. Yeah, it's Jordan. Yeah.
It's Jordan is not easy. I think probably not, because if codaric dimension negative, right? So
yeah.
If you assume minimal model program, so either you have some funnel fibration, but once you have some funnel thing, for example, you have this P1 fiber space. If once you content this P1, then automorphism of P1 already is not Jordan. And it is
sure.
a subgroup of the automorphism, right?
No, but it's the automorphism of the whole space.
If automorphism whole space is Jordan, then its subgroup is automatically Jordan. So I'm saying, for example, if you have some P1 fibration, but this automorphism of P1 is already not Jordan, but a subgroup of the large group. So the large group.
But how do you say the automorphism group of P1 is contained in the automorphism group of the full space?
You just suppose you have some fibration. Suppose you have some fibration, then you consider fiber-wise the automorphism. Fiber-wise means you have S to C. So that's the exact sequence. So you have some fiber-wise automorphism, then it will give you a subgroup, and the quotient is automatically a subgroup of automorphism of base.
Okay, so maybe in other formulations, so if you take a final variety of beacon number 1, so can you classify when this automorphism group is Jordan?
For surfaces, it's just P2, right? This is easy.
No.
For high
dimensional, P2 is not. It's not Jordan.
Yeah, for high dimensional, I don't know. For high dimensional, is there a classification for high dimensional funnel?
No. Beacon number 1 is quite hard. Yeah. So in particular, this would imply this final variety must be not rational or
okay.
Non-rational.
I see. Okay.
Then there should not many examples. I don't know. Okay. Thank you.
Okay. So no more questions?
One more question. Sorry.
Okay. Go ahead. Yeah.
Yes.
Hello. Yeah.
Yeah, because you are doing survey, so assume you can run minimum model program in dimension 3 or higher. Do you use classification? Otherwise, you assume resolution exists. Then can you do it in high dimension?
Resolution for threefold is okay, I think.
So you assume resolution, you assume MMP. So can you do the high dimension for auto and for birational? Auto may be easy. Birational case, I guess. Yeah.
But for three-dimensional,
we need a BAB maybe.
Yes, I need a BAB, but BAB for positive characteristic, I'm not sure if anyone studied it, or is there any difficulties for boundedness of three-dimensional or two-dimensional?
So it's a true modular BAB.
Yeah, I think so, because resolution argument seems works. Yeah, resolution argument works in three-dimensional case.
So in your project, you use classification or not? Surface?
Surface, no, just very little, because in Kodaira dimension negative infinity case, we use this classification either P2 or birational to C cross P1, because our bound layer is not very explicit. For example, if you are curious for explicit bound, then you need to use a lot of classification by specific case. I mentioned the work of Dolgachov, Kern, and Martin, Hui, some others for specific surfaces.
So sorry for long question. So for kappa equal to 0, you have a theoretical bound, but if we don't require effective, you don't need classification in kappa 0 case.
Kappa 0 case, we don't. But we can only show it is Jordan property, but we don't have a good estimate of these indexes. Yeah.
You need a bound of H2 or something?
Bound of H2, I think No, we don't need bound output. No.
Oh, okay. I see.
Also, sorry, Professor, I have one. Also regarding your question in email, I think this pseudo automorphism. I think we also don't know, like in positive characteristic, birational automorphism of minimal models of three-dimensional can be composition of flops. I think this was oversee. This was a professor's result, but over positive characteristic, it seems don't know yet. So we don't know the birational automorphism is automorphism of codimension 1 yet.
I see. Thanks.
Yeah. Okay, then I think yeah, it's time to close the session. Okay, let's thank the speaker again.
Oh, thank you.
Okay, so I think see you all. See you all in next AGEA Zoom seminar, maybe 2 weeks from now. Okay, now goodbye everyone.